we're going to compute the surface integral here. We've got the double integral over s of x squared ds, where s is going to be the unit sphere. And we've got a couple of tasks to do in order to be able to do this. One, we want to parametrize the unit sphere, and we also need to recognize that ds is not really what we're doing. We're not integrating directly with respect to the surface. This represents a different quantity. It's the cross product of a couple partials, but in order to find those, we need to first have that parametric surface. So let's go after that. We're dealing with the unit sphere here, so we're going to go ahead and parametrize this directly from our definitions of spherical coordinates. So you'll remember we have x equals cosine theta sine phi, y is equal to sine theta sine phi, and z is equal to cosine phi. And again, that's just coming straight from spherical coordinates. So we can parametrize this surface, the unit sphere then, by making a vector of r and phi using these exact definitions. So the x component is cosine phi, cosine theta sine phi. The y component is sine theta sine phi, and the z is our cosine phi. So now we have our parametric definition for the unit sphere. We just need to throw a range of values on there. If we want to get the whole sphere, we're going to allow phi to range from 0 up to pi, and theta is going to go from 0 up to 2 pi. And that'll be relevant particularly when we want to set up our integral. So now we've got that. This then allows us to go ahead and compute the ds quantity here. We've got r as a function of theta and phi, so we want to find the partials of r with respect to each of these two variables. So ds in this case is going to look like r sub theta cross r sub phi, and then we take its magnitude, and we're going to multiply that times a d theta d phi, or d phi d theta depending on what our needs are. So let's get those partials. And here r sub theta is going to be equal to the vector minus sine theta sine phi and cosine theta sine phi and 0, since the z component doesn't depend on theta at all. The partial of r with respect to phi is going to be the vector cosine theta cosine phi sine theta cosine phi and minus sine phi. And now it's just up to us to take the cross product and find its magnitude. Now I've done this already, so I could kind of save us a little bit of time here. R sub theta cross r sub phi and its magnitude is going to just be equal to sine phi. So now what this allows us to do is to set up our integral in terms of theta and phi. Going back up to the beginning, we've got the double integral over s of x squared, and we've got our definition here for x squared as cosine theta sine phi from our parametric definition of our surface. We've now figured out what ds is. It's going to be sine phi d theta d phi. So our total integral here is going to be the integral, the double integral rather, of x squared, where x again is cosine theta sine phi. So we're going to have cosine squared theta sine squared phi times that magnitude of the cross product. Again, we determine that to be sine phi. And then we need a d theta d phi. And let's throw in our bounds. We decided we want the whole surface, so our bounds are going to have phi going from 0 to pi and theta going from 0 to 2 pi. So at this point, it's really just like any other double integral we would solve, and we can use any method that makes sense for us to do that. Here, I'm just going to simplify down cosine squared theta, sine squared phi, or rather sine cubed phi, d theta, d phi. And because these are two independent functions, one of theta, one of phi, and I've got constants throughout my integral here, I can actually separate these into two separate integrals. I'll take the integral from 0 to pi of sine cubed phi d phi, and we'll multiply that times the integral from 0 to 2 pi of cosine squared theta d theta. And so at this point, we can run these through a computer algebra system, and we can figure out then from there what the value of our surface integral would be.